Section 5 is called bases other than e. So we're getting away from having e to the stuff, and we can get into things like 2 to the stuff, or 3 to the stuff, or anything to the stuff. That's what's going on in this section. So remember, the base of natural log is e. It's log base e is the natural log. Use this information plus the fact that e to the natural log of x is equal to x. If we do all that, we can write this definition. If a is positive and real, and x is any real number, then the exponential function with a base of a is this right here. A to the x equals e to the natural log of a times x. Do you see how that works? Why? Why does that work?
If we have an exponent of like the natural log,
Yeah.
exponent inside the natural log,
Uh-huh. All right, so you're saying that this x was an exponent on the a, and we just brought it down. That's right. So how do we go from here to here then? E and natural log are inverses, so they wipe out, and I'm just left with whatever this was. So it becomes a to the x. So this definition here hopefully makes sense. Okay, a little refresher on how to work with like bases and their exponents from Algebra 2. Anything to the 0 power is 1, of course. If we are multiplying like bases, meaning the numbers down at the bottom are the same, then we add the exponents. If I'm dividing like bases, then we subtract the exponents. And finally, if we raise a base with an exponent to a power, so powers to powers, we multiply the exponents. Keep those in mind for this section and always. So this section and subsequent sections from here on out for pretty much the rest of the course start to get into some interesting, more real-world type problems. And here's your first of those real-world type problems. Half-life type problems. The half-life of carbon-14 is 5,715 years. You start with a sample size of, how do you read that? S naught, yeah. Say it fast. How much will be remaining after 10,000 years? Well, this is a pretty standard type of problem. You've seen them before, probably. Once you learn how to set it up, you can do any of these problems. So one way to remember this is the basis of this problem is half-life. That's what they're asking you to do. So therefore, since it's half-life and the basis of the problem is half-life, then the base is going to be 1/2. I don't know, that's how I remember it. The exponent holds the time variable, but you write it as it compares to the overall half-life of the sample. So how much time has gone by relative to the half-life of the sample. So in this case, the half-life is 5,715 years. The initial time is always now, unless they otherwise have stated that. So call it now, and then in the future is the result of your problem. The beginning sample size is multiplied onto the exponential function. So whatever that number is, that constant, gets multiplied on to the 1/2 to the whatever power. You wind up with this result. So in this particular problem, apparently the half-life of carbon-14 has changed to 15. So it should be T divided by 5715. So notice what happened. We have the initial sample size times, we're doing a half-life problem, so the base is 1/2 to the amount of time that's gone by relative to the half-life of the sample. So T divided by 5715. If you can remember these sorts of things here, then you can set up any half-life problem that you might be presented with. So then from there, you just plug in values, typically, and solve. So let's have our initial sample contain 1 gram of carbon-14, and we'll use the updated version of the half-life. How much will there be in 10,000 years? What do we do? So yeah, what's S naught? 1. 1g. Times 1/2 10,000 divided by 5715. That's it. Enter it into your calculator and you get your answer, 3 decimal places. That's going to be pretty close to, what, a quarter? Because 10,000 divided by 5715 is probably pretty close to 2. 1/2 squared is about 1/4. 1/4 times 1 is 1, so right around a quarter. 2973, so 0.297. What? Grams. Yeah, because 10,000 divided by 57 is going to be less than 2. So after 10,000 years, that's right, this much carbon left. Now, the interesting thing is, we used 1 gram, but if I wanted to use 100% of a sample, 100% would turn into 1. So therefore, this is also a percentage because of the fact that we used the 1 sitting here. So after 10,000 years, 29.7% of the sample is remaining. I mention that because it's possible that they give you, in fact they do give you, problems that involve percentages. So you'll want to understand how to work with percentages, okay? 100% of a sample is a 1 sitting right here. All right. We need to remember changing a base for any log function. So log base a of x is equal to 1 over the natural log of a times the natural log of x. I think we knew that already. Which I can rewrite as this. This is exactly the same as that. Note, very important note right here, that the natural log of a is a constant. A is a base. It's not a variable, it's a number. So the natural log of a number is also just a number. 1 over that is still just a number. It's a constant. They're all constants, with the exception of that x. I want you to note that because when you wind up taking the derivatives of things like this, you need to know that that's a constant. The usual rules for log functions still apply. Log base a of 1 is equal to 0. We know that, right? We know why? Okay. Right, remember that this is the base, this is the exponent, and this is the answer. A to the 0 is equal to 1, so therefore log base a of 1 is equal to 0. We can split, we've talked about that. We can bring the exponent down, we talked about that. We can split division into a subtraction problem, and we've seen that before also. Some other true stuff down at the bottom. Y equals a to the x. The IFF is not a typo. That is if and only if. That's shorthand for if and only if, in case you've never seen that before. X is equal to log base a y. So that means if we have this, we can go this way because of that if and only if. And the way that's written, we can go this way also. If I take the log base a of my answer, I get my exponent, just like I do up here. That's all that's saying. A to the log base a. Those are inverses of each other. So they wipe out and I'm just left with x. As long as x is positive, that's the case. Log base a to the x. Log base a, the x can come out front here. Log base a is 1, so I wind up with just the x on that one also. This one's true always. So I have all the properties listed on the left, and we have a couple practice problems on the right. We want to solve for x. So on that top one, what do we need to do? Looks like straight out of pre-calculus right here. No. Yes. 1 over 81 is the same as 3 to the negative 4th power.
Oh yeah, we gotta make the like bases.
Make like bases. And now that I have like bases, what's x equal? X equals negative 4. Yes. How about the second one? No. What? No. 2? Two is the base. No. No. Well, okay. So you want to apply a base of 2 to both sides, is that what you're saying? Okay, because then 2 to the log 2 turns into what? X. X equals 1 over 2 to the 4th, which is? There's your answer. The base, the exponent, the answer. The base, the exponent, the answer. You could have just rewritten it, yeah. But the rewriting, actually, the math that goes on behind that is I applied this base to both sides to put both of these into an exponent. And once that happened, 2 to the log 2 wiped out, and I was left with that x. 2 to the negative 4th turned into 1/16. So that is the math behind rewriting this look to get into that. So I'm glad you guys went that way. Okay? Shortcuts are no good unless you understand the math. All right, let me see if I can zoom in here. Okay, differentiating with bases other than e. These are rules that you need to know, which probably means you need to memorize them. You need to work with them as much as possible so that they sink in, just as sunk in as the product rule, quotient rule, and chain rules are for you at this point. In fact, the regular derivative is sitting over here. The chain rule is sitting over here. If you memorize the chain rule and understand that you don't need the chain rule when you're just looking at an x sitting right here, then really you only need to memorize 2. Because these are exactly the same. The derivative with respect to x of a to the x is equal to the natural log of that base, which is just a number, it's a constant, times a to the x still. The derivative with respect to x of log with a base of a, x, is equal to 1 over the natural log of a times x in the denominator. If I'm using the chain rule, then that means I have some sort of function sitting here aside from just x. Anytime there's anything other than just x in the exponent, then you're going to make u your exponent, and you wind up with the natural log of the base a, same as before, a to the u, same as before, but then since you use the chain rule to get there, times u prime at the end. Same thing is true for log base a of some function. Make that function u, and you wind up with 1 over the natural log a times the original u that you had, but then times u prime at the end, and then you simplify from there. So really, like I said, there's only 2 rules that you absolutely have to memorize. The other 2 come from a very simple version of the chain rule. So if you memorize the chain rule ones, you should be good. So let's find the derivative of y equals 2 to the x. I don't need a chain rule here, so I'm just going to use this guy. The derivative of a to the x is equal to the natural log of a times a to the x. So therefore, y prime equals natural log 2, which is just a constant, times 2 to the x. And I'm done. There's lots of different ways you could write this here. In parentheses kind of makes it pretty clear what's going on. Let's go to this one down below here. Chain rule. So what do we got? natural log of 2 times 2 to the 3x, and u prime is 3. So now I need to try to simplify that somehow. I don't have a 3x anywhere. Y prime equals, the 3 can be written out front. 3 natural log 2 times 2 to the 3x. It's possible that at this point they would say, well, I could write that as an exponent, 2 to the third, which is 8. And then you'd have the natural log of 8 times 2 to the 3x. It's possible that someone somewhere might do that. But this is a perfectly appropriate answer right here. Yeah, so let's take a look at this one. Is this a chain rule problem? How can we make it a chain rule problem? It is a chain rule problem, because you don't have just log base something x, right? We have log base something, something. Log base 10 of something. So u has to equal cosine x. I'm taking derivatives, so I'm going to write u prime. Negative sign. The derivative of cosine is negative sine x. Okay, so now that we know that, we can apply this rule. So y prime equals
1 over the natural log of 10 times cosine.
Okay?
Times
So we have 1 over natural log 10 and then cosine x times, times what? Negative sign. Rewrite it. Negative sine x on top over natural log 10 cosine x. Sine over cosine is tangent. So you could actually continue and write negative tangent x over natural log 10, which is just a number. That would be totally simplified. It's possible that you might see that as the answer instead, just so you know. The advice that you're given with functions that deal with logarithms is to split as much as you can before you try to tackle. So properties of logarithms, I have division going on here. Y equals what? I'm actually going to leave the square root alone. Log 3 square root x
minus log base 3 x cosine.
Okay, now I'll try to take the derivative. There's a reason why I left this alone.
So the first one, u equals x.
All right, so we're going to let this be u right here.
So we get 1 over
U prime equals
1/2 x to the negative 1/2.
So 1/2 x to the negative 1/2 is that. Right? Okay. So now we can take this derivative right here.
So we get 1 over natural log of 3 times u, which is the square root of x, times u prime, which is
times u prime, which is 1 over 2 square root x, like that. And we have this minus sign here.
For that one, u prime equals 1.
So on this one, we also have a u situation. So let u equal, and you could use a different letter if you wanted to. That'd be fine. You could use v. Typically, we'll go to v. But u is fine. So x plus 5, which makes u prime equal 1. Kind of easy. So what do we get here?
1 over natural log of 3 times x plus 5.
Times u prime, which is 1. All right.
Now we can
Simplify. And this is why I left the square root of x alone. Had I not done that, everything would have worked out just fine. We still would have wound up with just x. But now we can clearly see that that becomes what? Just x, yeah. So y prime equals, we have 1 over, for this term, 2 times the natural log of 3 times x. I'm going to think ahead here. Minus 1 over the natural log of 3 times x plus 5. Yeah, we need to continue simplifying this one. So we need a common denominator. We need an x plus 5. And we need a 2. And we need an x. Does that get it done?
Yeah.
Okay. So now I can combine. Y prime equals, the top here is x plus 5 minus 2x divided by this common denominator, which is 2x. Do I want to multiply all that out? I could. The question is, do I want to? And I'm going to distribute the x's in and the 2, but I'm going to leave. Actually, I'll just distribute the x's in. So I have 2 natural log 3 times x squared plus 5x. So that's a constant times some stuff. Okay. And then y prime equals, combine like terms here, looks like 5 minus x to me over 2 natural log 3 x squared plus 5x. Good enough right there. So that was differentiating, now we're integrating. When you're dealing with an exponential function, convert to a base of e before integrating. Using a to the x equals this guy that we learned earlier, which hopefully made intuitive sense to us. You can convert using that. Or just integrate using this formula right here. The integral of a to the x dx is equal to 1 over the natural log of a times a to the x plus c. Easier. So for example, integrate. The integral of 2 to the x dx. What do we get? So 2 to the x. There's your answer. This is a rule right here that I've underlined that you need to know. There's a chain rule that goes along with that. Probably just multiply times u prime. No, not when we're integrating. You ready? Here we go. If it'll let me. There we go. The general power rule still applies to derivatives that we're taking. The derivative of x to the n is equal to, bring the exponent down to base, n minus 1. the derivative of u to the n is equal to, bring the exponent down, the base, n minus 1 times u prime. That's all still the same. So if I take the derivative with respect to x of e to the e, what do I get? Nope. 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 What is e? A number. What is e? This number here. A number. So we have a number to a number, which is a number, and the derivative of a number is 0. What about the derivative of e to the x? Is e to the x. That was the whole point of e to the x. It's its own derivative. But what about x to the e? The answer is sitting right in front of your face.
The answer is just
No. No. E times x to the e minus 1. We're using this rule right here. E is just a number. Okay, what about y equals x to the x? That's a good one. It's one we need to know, and we're going to save it for next time.